Thank you, Ross, and thank you, Nicola, for letting me take over. And of course, Mark is a smart guy because he basically introduced some topics of this talk right away, which will also contain data management. So let me quickly introduce Mark to you. Dr. Mark Dörr is head of the LARA Platform, mostly used for protein engineering, and he comes from the Institute of Biochemistry in the University of Greifswald in Germany. And he works in the group of Uwe Bornscheuer, whom some of you maybe know for his protein engineering efforts. And without further ado, Mark, I would say yours the screen.
Thanks a lot. Do you hear me?
Yes.
Yeah. Okay. Okay. Yeah. Very repressive. I have an echo. 1 second. So how's it now?
We can still hear you. Yeah.
Yeah. Now it's good. Okay. Yeah. Very impressive, Rosalind. So we are a very small group in comparison to what you have. But I still want to show you what you can do or what we do. So I'll quickly share my screen. So do you see it? Yeah.
Yes.
Okay, very nice. Yeah, thank you, Johannes, for your introduction and having this opportunity to present what we achieve or are achieving or trying to achieve in our platform in Greifswald. So where's Greifswald? Just for all that are not familiar with Greifswald, it's in the very northeast of Germany, at the coast. A very nice place to live. And we have this robotic platform. It's designed for protein engineering and screening. So quite similar to what Rosalind is doing. Just that you have an impression of how it looks like. So we have this central robot arm that it can address 4 incubators, a centrifuge, 2 plate readers, and then a pipetting robot and a carousel. And the processes we run, I will not show you the full film, just that you have an impression of the workflow. The full film or movie you can download here or watch it at this our webpage. So we have colony picking process, then we grow our cells, we have induction protocols, then we centrifuge our cells, we can wash the cells and lyse the cells, and then do assays, enzymatic assays with it, and further analysis of the data. So this is the overall very simplified workflow or the modules we are using, and what kind of research are we doing? So we have this protein engineering topic. We try to screen for new substrate scopes and altered substrate specificity. It's really very general in the sense because our projects are constantly changing. So it's so we have not a fixed theme, but we have like a set of, let's say, 5 different enzymes that enzyme classes where we have much deeper expertise, but from time to time new projects appear, and then we have to reestablish everything. Then we look at enzyme stability by using directed evolution approaches, and we are working in the range of 10,000 to a few million variants, usually more in the range of 10,000 molecules. Okay, and then a little bit what type of chemistry we are looking at, or biochemistry we're looking at. One main branch is our transaminase screening. So we look at finding new transaminases, doing this reaction where you have either a kinetic resolution. So you start with a racemic mixture of an amine, and then you cleave or deaminate only one, and the remaining one is the desired, which you have then hopefully in a very high yield, but this unfortunately only can yield to maximum 50%. A better approach is, of course, the asymmetric synthesis, where you start from a ketone and then you hopefully form with a transaminase, you form in the desired amine in a very high product yield. So by that you can make such product landscapes like this one here. So you can, for example, look for different ketones and then screen them against different enzymes, transaminases, and then you get a map of which enzyme best transforms this ketone, for example. Such things. And then another nice project was the screening for these these cars here. So we screened for the decarboxylation of this bulky carboxylic acids, making sorry, not decarboxylic, reduction of these to aldehydes, so bulky aldehydes with dye assay, and then forming a yellow dye when things are converted. By that we found nice new variants. We are using for most of our enzyme screenings and the split GFP assay for specific activity measurements. So the idea is that if you have like a multi-titer plate with a lot of enzymes produced, the quantification of these, you need to quantify these enzymes before or while or after you measure the activity, because sometimes you produce in one well a lot of enzyme, but it's not very active, and in another well you produce not so much enzyme, but it's very active. But and then you need to normalize that, and the normalization happens with an addition of a larger part of the non-fluorescent GFP, which is lacking this single beta sheet here. And this single beta sheet, this is attached to our enzymes, and if they combine, you can measure the fluorescence. So they are measuring again, and this fluorescence is proportional to the amount of protein you have in your enzyme. So this is a way to quantify. When we started, many of these processes had to be done manually. So manual project planning, manual project design. The execution is done with a proprietary software, and then we had manual data collection. We didn't start with Excel or something. We already established an R pipeline for that at the very early stage. And now we are moving towards Python. I will come to that in a moment. And finally, data evaluation was also done manually. So, but this was very tedious, and we produce, as you know, a lot of data with such platforms. So we have our initial idea was just to invent tools and make them open source, that this problem can be overdone. And here is our solution, or our way, or our approach to this. So we invented this LARA suite, which consists of modules. So it's like a microservice architecture, if you want. Modules for planning, for process design, for process execution, with data collection, data evaluation, and visualization. And just that you have an impression of how it's designed. So it's a kind of middleware, if you want. So we have on the one hand your device like balancers, robots, pH meters, or whatever. You have your process design, your project planning, and these communicate with a central database and this suite of programs to plan everything and then execute your processes and feed back your data back into the database. And this database, this suite is also connected to the internet, so you can retrieve information from PDB or PubChem and combine this information with your information and make a much more valuable data processing. So here are a few modules that just that you see what is already implemented. So we have this for planning modules, process design, process control, data collection, evaluation of data, people management, and compound and device databases. We are using right now very much Python 3 as our standard in JavaScript for the language, and very important is our CELA communication protocol that we are using in Animal as a standard for saving the data. So we have this language, one language for all paradigms. So we try to use as little different programming language that someone who is not experienced can immediately start and understand the module and modify it if you want. So one word to CELA. We are very engaged in making this standard, CELA standard. It's a lab communication standard, an international standard for all devices. So there's a currently very active community working on that, and I'm the maintainer of the Python repository for that. So if you have questions to the Python implementation, you can ask me. And it's for a standardized communication of all kinds of lab devices. So once you have this driver, then it's very simple to communicate to from like a process management system or LIMS system or databases to get the data and to start a process on these machines to get, for example, the weight of something. Very, very simple way to communicate. So worth looking into it. But this is not all what you need. You need also a language that describes processes. And so it's not done when you have the communication. You also need to describe a little bit what is going on your platform. And for that, we are currently very actively developing this Python lab language, which is a kind of universal lab automation language. We are hoping to use in our platform. So this is a very, very recent development. And the interesting thing about it is it's platform independent. So you formulate your processes. So here's a very simple example. So for example, move a container from start position to nest position, or incubate from incubate container 1 for this incubation duration, which is a variable set here. So you formulate all these processes in a very abstract manner, and then you have like a mapping of this process into your real world system. Just to quickly demonstrate you how this works, I prepared a little demonstration. I hope I can show you. So I just need to move my screen. See, do you see my terminal?
Yes.
Yeah. Okay. So here's a very simple process where you incubate something. So the incubation duration is set to 6,000 seconds. And then you do a plate reader process, for example, with a process name. The process name is OD600. And then you incubate another time, and then you run the process again. And then if the average absorbance is larger than 2, then smaller than 2, then continue incubation. otherwise do something else. Just that you have an impression of how this looks like. And when I run this process, oh, sorry. So when I run this process, it's just a simulation. But what you see here is that it now calls real devices like our cytomite, our varioscan, etc. So it maps what we abstractly specified into our system, and then executes it and communicates through CELA to the devices and does something. Just so that you get an impression of how this all works. Okay. So here's the overall process. So you have your representation of the process in an abstract language. Then you map that. Then you have an orchestrator, which you just saw as a demo, and this calls CELA devices on your device, local device. So that's the nice thing. So the process can be transferred to any robotic platform in the world, and then if you have the right mapping, then you can immediately run it. That's the overall goal of this project. And then another very important module is the lab data reader, which Nathan already and Johannes already saw a little bit. This is a project which came out of the need that many devices, they don't provide standard data in a standardized form. And this lab data reader has modules to read the data, transform it into a standardized data format, like for example, pandas data frames for Python or Animal, and then you don't need to understand how the reader the file format is produced. You can just use the reader and include your files, and you get it in a very rich data rich format into your pipeline as a kind of plug-in system. Animal is one way of storing this data. Just that you know that this exists, and there's a current application as becoming an ASTM standard. It's an XML-based standard to store any kind of analytical and process data. It could be HPLC, GC, even screening process can be projected into this language. So by doing this, we have now then the LARA suite or modules for the project planning, Python lab for the process design, CELA for in the scheduler you saw for the process execution, Reader for the data collection, and Python lab also possible to evaluate data. So we can use this language also describe evaluation steps like doing accumulation of data or doing averaging or whatever. And then we expose this data as BARQL endpoints to other external labs. So with a standard ontology and semantic based description of the data. So I think I will skip the machine learning part. So we are having partners with TU Berlin and other groups that do machine learning. One important project is the Kiwi Biolabs, which aims to combine two labs like the Technical University of Berlin with our lab through these standardized protocols using IE and machine learning to control the platforms. And for that, of course, all this, what I explained to you, so this language, this orchestrating tools are required to control the robots automatically and design the process. Another interesting initiative is this NFDI initiative. So we are in the CAT part, catalytic part, but there are much more. So it's a huge project of the Deutsche Forschungsgemeinschaft. I think it's around 300 million euros funding, and it's about standardizing data communication and exchange of data. So this is a very important project. Okay, to sum up, I tried to have convinced you that this designing of a complex or let's say integrated open source infrastructure will help to make data accessible or evaluation much more easily accessible and easily to combine also different, make it possible to combine different labs and exchange data in a standardized way, and hopefully such standards like CELA and Animal will in the future be much more spread and used, and by that it's much easier to make new, much more complex protocols in science. So finally, I would like to thank you people like my PhD student Stefan Mark helping me to program the scheduler, Stefan Born at the Technical University for all these nice comments on or his helping me with the architecture, the groups of Peter Neubauer, Johannes' group, of course, and Uwe's group. They support us also very much, the CELA team and the Animal team, and we are funded by the DFG mainly, and the BMBF. Yeah, by that, thanks for your attention, yes, and hopefully you have some questions.
Okay, thank you very much, Mark. You also get a round of applause. And of course, I have questions myself, but I will be polite and hold back. And there's a question from Biomics, and he's asking, are these XML storage SQL or no SQL based? Okay.
I mean, everything you can of course store in databases and relational databases. So it depends. So what we are heading at is a graph database. So the representation of or storing all the data in a graph database, because this is the natural let's say way of storing very hierarchical, very interconnected data. But if you just want to have like an archive of all your measurements, like all your GC or all your HPLC measurements, it's also very doable and easy to just push this data, stream this data into a file storage and save this as an XML-based, file-based storage if you want. So it's really up to you. So the design is very open in which direction you will move your data. I hope this answers the question.
I hope this too. The second question is, he also asked, and I'm not sure if I get this, is there a template for processing machine learning and AI data, I guess? I don't really, so let's skip this question because I don't fully understand it from how it's asked. Maybe Biomics can ask again. So there's another question from Giovanni, and he asks, how difficult is it to develop drivers for lab equipment, given that most of them have proprietary protocols or APIs?
Yeah, very good question. This really depends on two things. The first thing is how much it is documented by the vendor. So if you have no documentation of the interface, then it's very hard, of course. Then you have to hack into these devices. One opportunity is to talk with them, because they are right now very open to CELA 2. So a lot of vendors realize that this is an upcoming standard. if you have documentation, then we have provided in the Python repository a very convenient tool. You describe your features of your device in an abstract description language. It's XML based, and this will be compiled into a skeleton of Python code that can already be run in a simulation mode. And the only thing you then finally need to add is the interface communication. So for example, if you're using serial connection or USB connection, then you add into this code just the lines that communicate with the device on the hardware level. And this makes it very fast, and you can make like a nice LARA server in 1-2 hours, just thinking about the features, writing them down, and then run the code, get generator, and you have a running LARA server and client system.
Okay.
So it really depends on the complexity and the documentation of the device.
Okay. So thank you very much, Mark, and thank you for everyone for asking questions. Due to the time, and we'd kind of like to finish in time, if it's okay, I would stop this here. Of course, all the speakers, I'm sure, will gladly and happily reply via email. And I'm sure there would be very nice discussions about all of these topics that are now popping up as questions. But for a closing remark, I'd like to hand over to Paul Freeman, and all the stage is yours.
Thank you, Johannes, and thank you, Nicola, for organizing this wonderful webinar, and also for Rosalind and Mark, who gave 2 absolutely superb talks. I really enjoyed them. I think the Global Biofoundry Alliance is a wonderful opportunity for people to share, thoughts and ideas, and we're hoping that this webinar series will grow. And the way it's working is there's one in North America, one in Europe, and one in Asia, and they just cycle around, and then all of them will be put up on either a YouTube channel or on a virtual web-based platform for people to access if they didn't get to see it. But I hope these webinars really stimulate more interaction between the community, because some of the stuff we heard today was really terrific, and absolutely pertinent to what we're all trying to do, which is to make these biofoundries really efficient and work, to increase our capabilities in biotechnology and other research areas. So it's really terrific. And finally, what I'd really like to thank is Nathan Hilson. I daren't ask you the time, but anyway, thank you so much, Nathan, for hosting the webinar through some last-minute hitches. I really appreciate the Lawrence Berkeley National Lab stepping in at this final moment. So thank you again for being with us, and thank everyone for listening. And I hope we continue the conversations. Again, Johannes, Nicola, thank you so much. And I pass it back to Nicola or Johannes to say the final end.
Okay. Then I go first, so Nicola can be the last, closing everything off. So also thank you, Mark, thank you, Rosalind, for being here. And I fully also what Mark showed, there's a software group of the GBA where such things can be addressed, and it's great to work with you together. And thank you everyone for attending.
Yeah, thank you everyone for attending. We'll just remind you that this webinar will be recorded on the GBA website, so do share that link with anybody else that you think will be interested as well. Bye everyone.